Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we're going to continue with our circles chapter, and we're going to talk about arcs of a circle in 10-3. Now, an arc of a circle, gentlemen, okay, consists of 2 points on a circle and all points on the circle needed to connect the points by a single path. So what that means is, if I have this circle here and I have 2 points or 3 points or 5 points, the section that connects this point with this point is called the arc. It's basically a part or a percentage of the circumference. The arc center, okay, is the center of the circle of which the arc is a part of. That is the arc center. And a central angle, which we have already talked about and discussed, okay, forms basically the arc. The central angle, whose vertex is at the center of the circle, basically forms the arc. So in this particular case here, we have circle O. And we have radii OA, and we have radii OB. And the central angle here is angle AOB. This central angle, when you connect it on the circle itself, creates this arc AB. How do I name an arc? We put the 2 letters and we put a little arc over it. Okay? Now there's a lot more to this than that, but we need to start, of course, with the basics. So again, an arc consists of 2 points on a circle and all the points on the circle needed to connect the points by a single path. The arc center is the center of an arc, is the center of the circle, of which the arc is a part of. And a central angle is an angle whose vertex is at the center of a circle. Okay? Now, you have a minor arc and a major arc. A minor arc is the measure of a minor arc is less than 180 degrees and includes all points on or between the sides of the central angle. So just like I described in the slide before, I have this central angle AOB. The A and the B, when connected, creates this arc. Since this central angle is less than 180 degrees, the arc is less than 180 degrees, and therefore it is called a minor arc. And that is how you would write a minor arc. Consists of 2 points creating that arc. The major arc, my friends, okay, has a measure that is 360 degrees minus the minor arc measure. And it includes all points on or outside of the central angle. So let's put this to make a little bit more sense. The minor arc is in red. The major arc will be this guy here in blue. Since the major arc encompasses 3 different points, you would write the major arc as, in this particular case, ACB. Now, how do you find the measures of these? Well, if I said, for example, that this central angle is 60 degrees, that means that the arc measure is 60 degrees. And we're going to show you why now in a second. And then that means that this arc measure, the major arc, is 360 minus 60 degrees. So this would be 300 degrees. So minor arc is less than 180. The major arc is 360 minus the minor arc. Okay, so far so good? I'll take that as a yes. Okay, now a semicircle. Come again? Yeah, I just redid the example. Okay, thank you, sir. For example, find the measure of the major arc. If I say that the minor arc here is 40 degrees, what would the major arc be? 320, exactly. 360 minus 40 would be 320 degrees. So arc ACB, the major arc, would equal 320 degrees. Thank you, sir. Does that make sense, boys? All right. Now, semicircle. A semicircle is an arc whose endpoints are the endpoints of a diameter. Okay? So a semicircle is literally the arc of exactly half of that circle. So what do you think a semicircle's arc measure would be? 180, very good, because it is exactly half of the circle. Okay? Now, how can you recognize or tell that arcs are congruent? Congruent arcs, okay, are two arcs that have the same measure, hence congruent, but are not necessarily, sorry about that. Two arcs that have the same measure are not necessarily congruent arcs. In the concentric circle shown, remember what concentric means, circle or circles rather, that share the same center. In the concentric circle shown below, arc AB has an arc measure of 65 degrees. Arc CD has a measure of 65 degrees. However, CD and AB are not necessarily congruent. Why? The circles have different radii. If you notice, the radii of arc AB are AO and BO. The radii of arc CD is OC and OD. Okay? So you may ask, under what conditions then do you think two arcs will be congruent? Well, the arcs must be inside of the same circle, or if the arcs are on different circles, the circles must have congruent radii in order for them to be congruent arcs. Now, what am I talking about? Because this could be a little confusing. When we're talking about arc measure, we're talking about the degree of the arc. Arc AB in the example above and arc CD in the example above have the same arc measure. But arc length is an actual, bless you, is an actual distance. Arc length is a distance, and that's what's going to make them congruent or not. And I'm going a little bit ahead here, okay? But this is a very important formula. You're going to use it a lot throughout math. And to find the distance or the arc length, it's a very simple formula. It's the central angle over 360 times 2 pi r, which is the circumference. Or the arc measure divided by 360 times 2 pi r, which is the circumference. If you think about it logically, I have this circle here, and I want to find the arc length of CB. Isn't that just a percentage of the circle? Hence, the central angle divided by 360. That gives you the percent of the circle that is being encompassed in that arc measure. So arc measure is a degree. Arc measure is a degree. Arc length is a distance. And you find arc length by using the formula central angle over 360 times 2 pi r, or arc measure over 360 times 2 pi r. Yes, sir, my brother.
You're trying to find the measure of
The measure, we're going to talk about how to find the measure of the arcs in a second.
let's say you wanted to label a major arc if we only get 2 points on the circle. How would you?
If you only have 2 points on a circle, you have only a minor arc. You need a third point to determine a major arc. Thank you, my man. You're very welcome. Thank you. May I continue, brothers? Yes? Okay. Now, two arcs, like I said, are congruent whenever they have the same measure and are parts of the same circle or congruent circles. In this particular case here, arc AB and arc CD have the same measure of 60 degrees, and they're inside of the same circle. So the radii that created those two arcs are also congruent. So therefore, when they have the same arc measure and they're in the same circle, they are congruent arcs. So I can say AB is congruent to arc CD. Another way that you can tell if arcs are congruent, that means they have the same measure and the same length, the same distance, if you have two circles that are congruent. And by that I mean, of course, they have the same radii measure. Let's say that the radii here, let's say this is OE and OF, let's say it's 3. And I got OG and OH, and that's 3 as well. Now I can prove that arc EF is congruent to arc GH. Why? Because they have the same arc measure, the same degree measure, and since they're part of congruent circles, they will have the same arc length. Yes, sir. Oh, you're going to be using this a lot in proofs and in actual numerical calculations. Yes, sir. Absolutely. Okay. Are you with me here, gentlemen? Yes, no, maybe, kind of, sort of. I'm going to be throwing a lot of information at you today. Okay. Now, let's talk about some theorems. The central angle theorem. The central angle theorem states that the measure of the arc equals the measure of the central angle. So when I have a central angle that is x degrees, the arc that intercepts that angle is also x degrees. So what am I saying? So I have this center here, A, and I say this is 45 degrees, and I want to know the arc measure, because the arc measures a degree of arc CD. Arc CD will also be 45 degrees. So the central angle has the same exact measure as the arc that is intercepted by that angle. Give me 1 second, please. Okay. Now, I'm going to go above and beyond, as always, because I know that this is going to come to haunt you later, and I'd rather start you off early than little by little. I think this way it will assimilate a little bit better in your brain, and you'll be able to understand it better. Inscribed angle arc theorem. An inscribed angle is what occurs when you have an angle that is touching or intersecting one part of the circumference, one part of the outer edge of the circle. And in this particular case, when you have an inscribed angle measure, or an inscribed arc angle, I'm sorry, the measure of the arc equals twice the measure of the inscribed angle. So for example, if this angle here is 40 degrees, the arc that is intercepted by that angle would be 80 degrees. So central angle theorem, the central angle will equal the same measure as the arc that is intercepted by that angle. Inscribed angle theorem, the arc will be twice that of the angle that it is intercepted by. Very, very important. Very important here, guys. Are you with me? Yes, no, maybe kind of, sort of? Yeah? Okay. One more. Actually, there's quite a few more, but I'm just going to start you out with the basic three. Exterior angle arc theorem. An exterior angle occurs, as you see, when an angle is on the outside or exterior of the circle. And in this particular case, when you have an exterior angle, the measure of the exterior angle equals half of the difference of the measures of the two intercepted arcs. So what that means is that x here will equal 1/2 of A minus B. And it has to be in that particular order. Because if you can see, A is larger than B. So if you do B minus A, you're going to have a negative, and that is inaccurate. So what does this mean? So I have this circle here, and I have, let's say this is 80, this is 30, and I want to find x. Well, x will equal 80 minus 30 divided by 2, so x will equal 25 degrees. So central angle equals the arc that it intercepts. An interior angle is half the size of the arc that it intercepts. And an exterior angle is half the difference of the two arcs that it intercepts. Very important. This is not in your book. Okay, not in this section. So please make sure that not only you write it down, but that you understand what's going on here. You with me here, boys? Yes, sir. Oh, thank you, my brother. May I continue? Okay. Now, when we're relating congruent arcs, chords, and central angles, before we go over the theorems, I want you to understand a few things here. Again, AB would be a minor arc because it is less than 180 degrees. This bad boy right here is the central angle because it is the angle formed by the center of the circle. These two radii, okay, form this minor arc. The angle measure of this central angle will equal the arc measure of this minor arc. This bad boy right here is a chord, and arc ACB is what is known as the major arc. You with me? Remember this also, a little bit of past knowledge. If my radii is perpendicular to this chord, it also bisects that chord. You with me, guys? A lot of stuff going on in circles. Now, the real theorems that we got to learn for today. The intercepted arcs theorem. If two angles of a circle or of congruent circles are congruent, then their intercepted arcs are congruent. So we already saw this in the central angle theorem. If angle QOP is congruent to angle ROS, then that means arcs QP and RS are congruent. Because not only do they have the same measure, but they have the same length because they're in the same circle. They have the same radii. So if two angles of a circle are congruent, or of congruent circles, then their intercepted arcs are congruent. Okay? Does that make sense? All right. I'll take that as a yes. Next. The converse of the intercepted arcs theorem. It's the converse, guys. If two arcs of a circle or of congruent circles are congruent, then their corresponding central angles are congruent. So basically here, if they tell you that arc QP is congruent to arc RS, then angle QOP will be congruent to angle ROS. Very important theorems. Does that make sense? Okay. Let us continue. Central angle chord theorem. The central angle chord theorem states if two central angles of a circle or of congruent circles are congruent, then their corresponding chords are congruent. So what this is saying is if angle ACB is congruent to angle DCE, then chord AB will be congruent to chord DE. And of course, vice versa, the converse of that. The converse states, of course, that if the chords of a circle or of congruent circles are congruent, then their corresponding central angles are congruent. So that means that if AB is congruent to DE, then angle ACB will be congruent to angle DCE. A lot of powerful stuff here, guys. When you're doing your homework, you're going to need to know these. Okay? Is everyone with me here? Now, I do kind of apologize. I know that we're going fast, but that is why we have a video, and that is why you guys are in honors. Okay? So basically, what the converse says is if AB is congruent to DE, then angle ACB is congruent to angle DCE. This chord is congruent to that chord. This angle is congruent to that angle. And that's what's happening here. Yes, sir.
There was a proof where it only had chords, but the simple chords were grouped, and it didn't have like the didn't have this front, but it had the points in the middle. Could you draw the
Very good question. The question was, let's say that they just gave you a circle with segment AB and DE and they said they were congruent, but you had a point C here in the middle. With auxiliary lines, you can prove that CE is congruent to CD, which is also congruent to AC, which is also congruent to BC. And then now you can use the converse of angle-chord theorem. Since this chord is congruent to that chord, the central angles would be congruent, sir. And then from here you could state, you can go beyond that, and now you can even say that triangle ACB is congruent to triangle DCB because of side angle side. Because the radii are congruent and the central angle is congruent as well. Does that make sense? Good question, son. Thank you. We're good? Okay. Last two. The Arc-Chord Theorem and its converse. The Arc-Chord Theorem states that if two arcs of a circle are congruent, then their corresponding chords are congruent. So if chord QP is congruent to chord, if arc QP is congruent to arc RS, then chord QP will be congruent to chord RS, and vice versa. If you have two chords of a circle that are congruent, then their corresponding arcs are also congruent. See if I can squeeze them both in here. Yeah, so basically what this is saying is if chord QP is congruent to chord RS, then arc QP is congruent to arc RS. Yes, sir. No, because in the other one, I like your connections. The last theorem stated that, hold on please. So yeah, basically what he said was very astute. He said, Mr. Moll, since this chord is congruent to this chord, because of the central angle-chord theorem, doesn't that make angle ROS congruent to angle QOP? Yes. But then doesn't that activate the central angle theorem, where if angle QOP is congruent to ROS, then isn't arc QP going to have the same measure as arc RS, making those two arcs congruent as well? Yes, the answer is yes to all of that. They all piece together here. All of them piece together. That's why it's important to know all of them, because they may give you tidbits of some, and then you just fill in the blanks to create the rest. Yes, sir, my brother.
But you wouldn't be able to go from, for example, you wouldn't be able to go from like having those central angles, QOP,
Okay.
ROS. You wouldn't be able to go from there and say that arc QP is congruent to arc.
Absolutely, you can. If you know that angle ROS is congruent to angle QOP, you know then that arc RS is congruent to angle ROS. You know that QP is congruent to angle ROS. So by transitive property, QP would have to be congruent to RS. But you don't have to use transitive. In that case, you can use central angle theorem.
So like activates.
Exactly. That activates all of them. That's exactly correct. Brilliant question, buddy. Thank you. Good job. Very proud of you. Does that make sense, boys? Okay. A lot of excitement in the room today. Okay. Find the measure of the minor arc. The minor arc here. Okay, well, the minor arc here is AB. Isn't the central angle 102 degrees? So what would the arc measure of AB be? 102 degrees. That's it. We're not going to talk about arc length yet. Okay, but if I wanted to find arc length, if I did, it'd be 102 degrees divided by 360 times 2 pi r. I would also need the radius value, but that's the equation I would use to find the arc length. But right now we're just focusing on arc measure, which is an angle. Okay? It's just an angle. Not bad, right? What if I wanted to find the major arc? If I wanted to find the major arc, first of all, I'd have to have another point here, let's say D. And then I would say the major arc measure would be 102 minus 360, which would be 258 degrees. Does that make sense? Yeah? Okay. No, we're not done. Okay. We'll be done when we're done, guys. Yes, sir. Hold on. Let me see if I wrote that wrong. Okay, guys, and that is a mistake. It would be D is the midpoint of AC, and I apologize about that. Thank you, sir. So we have circle O, and the fact that, let me undo this as well. That is my bad. Well done, sir. D is the midpoint of AC. That's a given. Okay, so if we know that D is the midpoint of AC, what are we going to know? Very good. Arc AD is congruent to DC. Basically here, the midpoint of an arc divides the arc into two congruent arcs. It's basically the definition of a midpoint, but the definition of a midpoint can work for arcs and or segments. What else do we know since this is circle B? So far we know that this guy is congruent to that guy. What else do we know for sure? Yes, sir. No. Well, you did get it. Good job, buddy. Angle ABD is congruent to angle DBC. Why? If two arcs of a circle are congruent, then their corresponding central angle are congruent. If you know that arc AD is congruent to DB, then angle ABD is congruent to angle DBC. And what are we trying to prove here? We're trying to prove that BD bisects angle ABC, which we just did because of definition of angle bisector. Very good, buddy. Good job. Proud of you. That was sharp. All righty. And last but not least, what fractional part of a circle is an arc of 36 degrees? And how about of an arc of 200 degrees? What fractional part? If I have an arc measure that's 36 degrees, what fractional part of the circle is that? 1/10. Very good, guys. 36 divided by 360, that is 1/10 of the circle. How about of 200, guys? What fractional part is 200 degrees of a circle? You got 200 divided by 360. Get rid of these zeros. Divide 4 to both numerator and denominator. And you've got 5/9 of the circle. And what would the measure of an arc that is 7/12 of its circle be? Okay, think about it. If you have an arc that is 7/12 of means multiply, of 360, that is going to be 30 times 7, so it would be 210 degrees. Okay? You could make a proportion if you wanted to. Very proud of you, bro. Okay? Guys, a lot of information was thrown at you here. Please use your notes to complete the homework. Thank you very much. I hope you learned a lot and have a great day.